Okay, I will begin.
Invited.
Okay.
With that effusive introduction, I will begin.
So
All right, okay.
let me just introduce our today's speakers.
Okay.
Who I guess he doesn't need any introduction. You all know Keith Kearnes from CU Boulder, and he'll talk today about abelian minimal variety. Please, Keith.
All right, thank you, Peter. Thanks everybody for showing up. I'm going to start by trying to share my screen, and let's just see if that worked. Yeah. So.
Would everyone who is not the speaker turn their mics off? Thanks.
Okay, so I want to talk about minimal strongly abelian varieties. This is ongoing work with Emil Kish and Agnes Cendre, and we did most of our work last fall. We had a manuscript, very long manuscript, around November, and I did get a chance to talk about it at the Berkhoff seminar in Boulder in January, very briefly, just at a high level. And now I want to give a seminar level talk, which means I want to go into a portion of it and discuss some of the proofs. But this is about the classification, or the attempted classification, of all minimal abelian varieties, okay? And the topic that I'm going to discuss the proofs for are the strongly abelian case. So this talk is part of this larger project with Emil and Agnes. And actually Matt Valeriot was part of our earlier work. Many years ago, we worked on this project. The object is to classify all minimal abelian varieties. So everyone knows a lot of minimal varieties, and it's the full classification of varieties is impossible. The full classification of minimal varieties is impossible, but it might be possible to fully classify the minimal abelian ones. So we've divided our project into pieces, and the first couple of pieces are obvious, I think, sort of obvious. Look at a minimal abelian variety and show that it splits into one of two types. Minimal abelian varieties that are affine, those are the minimal abelian varieties that have a Moussev operation, or minimal abelian varieties that are strongly abelian. Now, when I say this is kind of obvious, what I mean is this split was known around 1990 in the case of locally finite varieties. It grew out of the work of Hobby and McKenzie and also Matt Valeriot in his thesis. You could determine that minimal abelian varieties have to split into these two types. Type 1 and type 2 is what they would call them in tame congruence theory, but we're not locally finite now. So it requires work to show this split takes place. And we did do that, and our paper has been accepted at the International Journal of Algebra and Computation. Now, if there's two types, you have to classify those, and you can do them separately. The easy case is the affine case, and the heart of the idea for this classification already exists in Agnes Cendre's clone theory book. She has some ideas there about affine clones. And so we do a little bit of work. We get new results in this paper, but this is the easy part. The hard part is what I'm talking about today: minimal, strongly abelian varieties. And this case, I'm assuming bounded essential arity. Okay, and the fourth case will be the unbounded essential arity. And the reason for this split is because we know how to do 3 and we don't know how to do 4. Okay, we would like to do all minimal strongly abelian varieties, and presently we can only do it if they have bounded essential arity. Okay, so I'm going to talk about that today, and let's make sure everybody's on the same page and understands the words I'm using. When I talk about varieties, I mean a class of models of a set of equations, like the variety of groups, variety of rings. When I talk about the essential arity of a variety, I'm using this epsilon symbol. Essential arity K means every operation in the variety depends on at most K variables in any model in the variety. Okay, so if it's a unary variety, all operations depend on one variable. The essential arity of the variety is 1. Okay. What does it mean to be abelian? There are lots of different ways of writing the definition down, but if you had to do it on slides, it's fastest if you just draw a picture and say this. If A is abelian, if A cross A has a congruence with the diagonal of A cross A as a congruence class. Okay, that's one way to express it. If you think of abelian groups, a group is abelian if the diagonal subgroup of the square is normal. Okay, and we can apply that definition to any other type of structure. That's not probably this is not the most primitive way to express this definition, but it's the simplest to draw. Okay, now what about strongly abelian? Strongly abelian algebra should be abelian. That means A cross A should have a congruence with the diagonal as the class, but it's A cross A should also have a congruence that looks like this. It's a congruence where every diagonal element is a singleton class, but every non-diagonal element is congruent to its symmetric pair. So pair little xy should be congruent to pair little yx. I want all of those to be in the relation, but on the diagonal, I want singleton classes. Okay, now that's not at all how the concept of strongly abelianness came up, but it turns out that if you put these two things together, it reduces to the standard definition. So you see at least that strongly abelian is stronger than abelian because strongly abelian has both of the conditions. Okay, so you don't need to know any of this for what I'm talking about, because whenever I want to use a property of strong abelianness, I'm just going to cite somebody's paper and say they proved this about strongly abelian varieties, so we use it. But this is just for, so you feel comfortable at this point. Okay, so examples. What's an example of a strongly abelian variety? Simplest example is a unary variety. The unary variety, all the operations have only one variable. By the way, I'm going to not talk about constants. I'm going to exclude constants from my language. They don't affect the answer, but they simplify some of the things I say. So I will just assume I never have constants. I will replace those with constant unary functions instead. Anyway, any unary variety is strongly abelian. So if you have a monoid and you look at the actions, the way that monoid can act on a set, you get M sets or M acts. Some, I guess a semigroup theorist might say M acts instead of M sets. I'm not really sure, but actions of M on a set. It's a unary variety, strongly abelian. Here's an example that's interesting. I like this example because it has bounded essential arity, and it's one of the simplest examples of a variety with bounded essential arity. If you take any semigroup and it's strongly abelian, it will satisfy this equation. But the collection of all semigroups that satisfy this equation is a strongly abelian variety. So the collection of all strongly abelian semigroups is a variety. It is this variety. It says a three-way product reduces to just the product of the first and the last factor. So any longer product always reduces to the product of the first and the last factor. And a semigroup theorist will tell you that a semigroup satisfies this identity exactly if it's an inflation of a rectangular band. Okay, now I'm going to draw a picture of this, but first let me get the next example down, and then I'll start drawing a picture. Diagonal algebras. A variety of diagonal algebras with a single diagonal operation of arity n is strongly abelian. It's this variety, you say that the diagonal operation is idempotent, and you say that D diagonalizes itself. And saying that D diagonalizes itself looks like this. It says if you apply D here to a column of distinct variables, and you keep doing it, always putting different variables in until you get the different variables here. So you get an n by n array of variables, and then you apply D to the results. So I really had a matrix and I applied D to the columns, and then I applied D to the results, you just get D down the diagonal. That's what a diagonal operation is. Okay, let me stop my share and share with the tablet. Mm-hmm. Do we see a tablet? Do we see a whiteboard, everybody? I hope
Yes.
so.
Yes.
Good.
Yes.
Let me say something about these semigroups that satisfy this. I said they're inflations of rectangular bands. So what is a rectangular band? Start with a set A and a set B and take their product. And here's the product set, A cross B. And I'm going to define a multiplication on the product set, which I'm going to take two elements in the product set and multiply them. The first one, let's call this A, B. And the second one, I'm going to call it C, D. And I want to multiply AB times CD. And the rectangular band rule is you take the first coordinate of the first and the second coordinate of the second. So you end up, this is the product. Okay, you go this way. So starting with this is the first factor and this is the second factor, the product is here. Now this kind of multiplication satisfies some identities. It satisfies the diagonal identities for n equals 2. That is, this multiplication is idempotent. And if you take a matrix and you multiply down the columns, let's say XY, and you multiply down the second column, and that's going to be ZW, and you multiply first column by second column, then you get the diagonal, which is XW. Okay? So that's an identity satisfied by the binary diagonal operation. If you put these together, you will find that you can derive this law, and from this law, you can derive these laws. Okay? So when I talk about, if you add idempotence. If you add idempotence, you're saying the semigroup multiplication is a binary diagonal operation. Now in my second example, I didn't have idempotence, and the effect of that is, here's a typical model of this variety. Typical model has inside of it a rectangular band, but then there are some other elements floating outside, and the squaring maps every element outside into an ideal, which is in a rectangular band, and then inside that ideal, the multiplication is rectangular. So that's the structure of that kind of variety. Okay. So let me stop that and go back to what we were saying. These are very reasonable examples of strongly abelian varieties. Wait a second. Why am I not? Okay, I'm not able to share anymore. Let's see. Maybe I am. Okay, I am sharing. Now I'm going to mention a strongly abelian variety that doesn't look like the ones above. This is an example that doesn't have bounded essential arity. The first one has bound arity 1, essential arity 1. All the operations have one variable. These have essential arity 2. Every product only depends on 2 of its inputs. Diagonal algebras depend on all n variables, but not more. Even if you compose D with itself, no operation in the clone depends on more than n variables. But the variety of Jansson-Tarski algebras has operations that depend on arbitrarily large arity. It has a multiplication. It has a left unary function and a right unary function. And the identities are the left part of a product is the left factor in the product. The right part of the product is the right factor in the product. And if you multiply the left part of an element with its right part, you get the element back. Okay, those are the identities for Jansson-Tarski algebras. And these are just the identities if you wanted a bijection between a set and its square. That if you map the square to the set in a bijective way, that can be thought of as a binary operation, a multiplication. If you map A back to the square, the inverse map, it has coordinate functions, which you can call L and R, and saying that these are inverse bijections are exactly what these identities express. It's a minimal strongly abelian algebra. It does not have bounded essential arity. That is, the product symbol, you can take longer and longer products and they all depend on each variable. Okay, so those are the definitions, and this is the theorem I want to prove, or outline the proof of. What are the minimal strongly abelian varieties that have bounded essential arity? I want to say they're the same as those that are categorically equivalent to a minimal unary variety. Let me just stop right there for a moment. If I have two varieties and they're equivalent as categories, and one is minimal, then the other is minimal. And if one is strongly abelian, the other will be strongly abelian. So I only have to describe minimal varieties up to categorical equivalence. And I want to say, it's well known that any unary variety, if it's categorically equivalent to another, the other variety must have bounded essential arity, but we're proving the converse for minimal varieties. If it's minimal, bounded essential arity, it will be categorically equivalent to a unary variety, which is necessarily minimal. Okay, that's the main result that I want to talk about. But you can go further. What are those minimal unary varieties? A variety of sets. Okay, set with no operations. It forms a variety and it's minimal, and operations depend on at most one variable. Or if it's not sets, it must be M sets, or almost M sets. There must be a simple monoid with 0, and V is categorically equivalent to a minimal subvariety of M sets, and it's the subvariety saying that 0 acts like a constant function. So you take any simple monoid with 0, you look at the M sets, that has some subvarieties, but the subvariety axiomatized by saying 0 is constant is a minimal subvariety, and every minimal unary variety is one of these two types. Okay, that's for today. The theorem was already proved 25 years ago, approximately, for locally finite varieties. Emil Kish, Matt Valeriat, and I worked on it, and Agnes Sendry worked on it, and we basically proved that theorem for locally finite varieties. Agnes used clone theory, and Emil and Matt and I used tame congruence theory, but we showed that a minimal strongly abelian variety is either categorically equivalent to the variety of sets or the variety of pointed sets. And this is, if you start with the two-element semilattice, that's a monoid that has 0, and you write down the identity of all M sets over the two-element semilattice, but then say 0 acts like a constant function, you just get pointed sets. Okay, so we phrased it this way before, but now it's better to phrase it in terms of monoids. So for everything I say today, you can assume I'm not talking about locally finite varieties. I'm talking about non-locally finite varieties, because the locally finite case is done and it agrees with the theorem. Okay, so here's the first stage. This is the first major stage. The first major stage was proved by Emil Kish and Matt Valeriat in the 1990s. They proved if you have any strongly abelian variety of bounded essential arity, it's Hamiltonian. And Hamiltonian means any algebra in the variety has the property that each subalgebra is a congruence class. Okay? So I'll just talk for a little bit here. Remember, the definition of abelian was the diagonal subalgebra of the square is a congruence class. So if you're Hamiltonian, every subalgebra of any algebra is a congruence class. So the diagonal subalgebra of the square will be a congruence class, so Hamiltonian applies abelian. And the question was whether the converse holds. If it's abelian, does it have to be Hamiltonian? Do all subalgebras have to be congruence classes? And it's easy to see just straight from the definition. It's not just the diagonal of the square that's a congruence class, but any equalizer subalgebra. The diagonal subalgebra of the square is the equalizer of the coordinate projection kernels of the square, but in the variety, any equalizer algebra as a congruence class. Any intersection of equalizer subalgebras is a congruence class. So if I start with the subalgebra and I intersect all the equalizer subalgebras that contain it, you get something called the dominion. This is what Isbell called it, dominion. So we're really saying every subalgebra is its own dominion. That's what this Hamiltonian property is. And the question is having diagonal subalgebras of square being their own dominion sufficient for all subalgebras to be their own dominion? And Kish and Valerius showed the answer to be yes for locally finite varieties, but no for strongly abelian non-locally finite varieties. There are strongly abelian varieties that are not Hamiltonian, but they showed if the essential arity is bounded, then it will be Hamiltonian. So this is a really non-trivial theorem. It's very close to being false. And they have a counterexample. If you delete probably any hypothesis here, if you delete it, this is going to be false. Okay, so they proved this in the 90s, and it's important for us. But before I say why it's important, let me just give you a way to restate it. This is a restatement of the Hamiltonian property in terms of the terms, properties of the terms, or properties of the identities of the variety. If you give me any term in n variables, there will be another term in n variables such that D diagonalizes T. It's the same equation you already saw, where I have an n by n array of distinct variables. I apply T to the columns and then D to the results. And it's the same thing as applying D down the diagonal. Okay, that's what it means to say that D diagonalizes T. Now, if every term T has a diagonalizing term, that is equivalent to the Hamiltonian property for strongly abelian varieties. Okay, this D doesn't have to be idempotent as it was earlier, but it will be idempotent on the range of T in any model in the variety. Okay, so they have this term characterization of Hamiltonianness. Let me tell you why Hamiltonianness is useful. This is the consequence that's useful for minimal varieties. And this refers back to a paper written by Ralph McKenzie in the 90s on categorical equivalence of varieties. So I'm starting with a variety, it's minimal Hamiltonian, and I have a unary term. And the variety does not believe U is constant. So it does not satisfy the identity that would express U interprets as a constant function on all models. Okay, so U is non-constant on every model because it's minimal. Suppose I have a non-constant U, a U that depends on its variable. Then there's some complicated thing that happens. There's a bunch of partial right inverses. They're unary functions. And there's a kind of mutual left inverse, which I call lambda. And you put it all together that if you take U and you right multiply it by all the rows, and then you left multiply by a big lambda, you get the identity back. Now, you could use your intuition from ring theory here. An example of a minimal Hamiltonian variety is a variety of modules over a simple ring. So let V be modules over a simple ring. That's minimal and Hamiltonian. Then let's say U is a unary term. That just comes from the ring. So I'm talking about a ring element. And when I say it's not constant, I'm just saying I have a non-zero ring element. I have a non-zero ring element in a simple ring. Then you want to say that the two-sided ideal it generates is the unit ideal. It's everything. How do you show that U generates everything? You right and left multiply U by various elements and add them up and you get 1. And that's really what this identity is saying. You right multiply U by a bunch of things, and this lambda collects a bunch of left multipliers on the different variables and add up the results. So this is really what you would express in the case of a ring. If U is a non-zero element, it generates the element 1 in the ring. But it's not about modules. This is about any minimal Hamiltonian variety. So that's a nice theorem, and I want to prove it. So here's how you prove it. let F be the free algebra on one generator in the variety. And I'm going to take the function U and apply it to F, the underlying set of F, and I'll get a bunch of elements back in F. Okay, these U of F is a bunch of elements in F, and I'm going to generate a subalgebra with those elements. Okay, there are cases. Is the subalgebra all of F, or is it less than all of F? Well, suppose the subalgebra is not everything. Then, because we are Hamiltonian, this subalgebra is a congruence class. So there is a congruence that has S as a class, and I'm going to factor by it. Now, because this is a proper congruence, it can't be the total congruence because S is not everything, and it's a single class. So this quotient is a non-trivial algebra, and it's in a minimal variety, so it generates the variety. This quotient generates the variety, but the entire range of U was contained in S, and I just collapsed S to a singleton. So in this quotient, U is a constant function. So the quotient satisfies an identity saying that U is a constant function, but this quotient generates V, and V does not satisfy the identity that says U is a constant function. So there's a contradiction there. And the conclusion is that S is F. Suppose S is F. So I take U applied to things in F, generate a subalgebra, I should get everything in F back. And one of the things in F is X. X is one of the elements that will be generated. So how is it generated? Because you applied a term lambda to a bunch of things which are U applied to a unary term. U applied to elements of F. So this equation is exactly the expression that this subalgebra contains the element X. So that's the proof, and it shows you why Hamiltonianness is a nice property when you're discussing minimal varieties. It says that everything, if it depends on its variable at all, it's essentially invertible. It's invertible in this weak sense. And this is an invertibility condition that came up in Mackenzie's paper on categorical equivalence of varieties. We say U is an invertible unary function. It's Mackenzie's sense invertible, that it has these partial right inverses. You multiply U on the right with these partial right inverses, and then you have this mutual left inverse, and you put it all together and you get the identity back. Okay, so I'm going to call this Mackenzie invertibility. Okay, so what we just found out is every unary operation that depends on its variable is a Mackenzie invertible in its variable. All right, and it's not strictly about unary term operations. I can take any U at all with many variables, and I can assume that it depends on one of its variables X, and just repeat this argument, and you can work with this, and we do in our paper, and you get exactly the same identity, except the U part has some parameters in it. Some U part has some parameters, but otherwise you get the same identity. And the conclusion is any term at all, if it depends on one of its variables in the variety, it is Mackenzie invertible in that variety. And that gives you a feeling of that these are, every term behaves something like a quasi-group term. If we had true invertibility, every term would behave like a quasi-group term. Okay, that's a very strong kind of conclusion. Okay. Now, we talked about diagonalization before, and this is another place where bounded essentiality comes up, is we said every term has a diagonal term, but in fact there is one term that serves to diagonalize everything. So the quantifiers are being turned around here. Before I said for every d, there exists a dt that diagonalizes it, and now I'm reversing those. I'm saying there exists a dt that works for every t simultaneously if you're minimal, strongly abelian variety, and you have bounded essentiality. So I claim that V has an idempotent term and it diagonalizes every term. And so I draw this picture for people who are getting bored at this point. This is my precious diagonalizing term. Okay. I want to say something about this. first of all, the first thing I want to say is it's not true. Okay, this theorem's not true. What I want to say is if I take a term, let me see if I have the diagonal equation here somewhere. Do I? No, I don't. Let me go back to it just so we can stare at the diagonal equation for a moment. This, for every term t, there's a dt, so that you can apply d to a bunch of t values and just collect what's going on down the diagonal with the operation t. Okay, that's the diagonal operation. Now, if I took a t and permuted its variables around, I have to change my d by permuting its variables around. And if t was independent of some variables, then that affects the d that works here. So this is really affecting the truth of this theorem. It's not quite true that this d diagonalizes every term, because if I take a term and permute its variables, it's not this d, but a d that came from permuting its variables. And if I have a term of fewer than k variables, it can't be diagonalized by a k variable term. It has to be diagonalized by its own arity. So I have to expand the arity of the term to put in fake variables. And I have to worry if t has more than k variables, I have to use this bound on essential arity to ignore some of the variables that it doesn't depend on to get it down to k to make this work. But the truth of this is true up to some form of variable manipulation. And I don't want to get into the details, but that's in the paper. The variable manipulation is handled in the paper. So let me explain why there's one term to rule them all, and that's an idempotent term that diagonalizes everything. So I want to find this special term. It diagonalizes everything. I have some term of arity k in the variety, but nothing of arity larger than k. So the strategy is to find a term of maximal arity k, find some term, who knows what it looks like, and I want it to be surjective for equational reasons. So when you interpret this term as a term operation on any algebra in V, it always comes out to be a surjective operation. Then, because every term has a diagonal term, I pick a diagonal term for a surjective term of maximal arity. And that will be idempotent on the range of t, which is everything. So it'll be idempotent. If we get surjectivity, the diagonal term for this special t will be idempotent. It will diagonalize this t, and then you just have to argue that it diagonalizes everything else. So that's the structure of the proof. But how do you find a surjective term of maximal arity? Okay, and this is where we look. We look at the Mackenzie invertibility equation. Okay, I'm going to start with a term of this u will depend on all of its variables, and there will be k variables it depends on. I start with a u of maximal arity and use Mackenzie invertibility in one of the positions, in one of the variables. So u depends on x and y bar, but I look at it's depending on x, so I have Mackenzie invertibility in x. Notice that the lambda that appears is surjective. Okay, lambda is surjective because there's an x on the other side of the equation. So if you take a model in V and you take an element of that model and plug it in for x, you can fill out these variables and get lambda of some values gives you that x. So every element of that model will be lambda of something. And that shows lambda is surjective on any model. So we can build surjective terms from the Mackenzie invertibility equation. But we don't know if they have maximal essential arity. If I could find just one of these lambdas whose essential arity is k, its diagonal term will satisfy this theorem. So I want to do that. I want to show at least one of the lambdas from the Mackenzie invertibility condition. I start with a u depending on k variables, and I go through and do the invertibility in every one of the variables and keep checking to see if one of those lambdas is of arity k. Okay, and we prove this by contradiction by assuming none of the lambdas have arity k. So I'm going to look at u. It has k variables. I do Mackenzie invertibility in all k variables. They produce k different lambdas, and I'm going to assume all of the lambdas that come up depend on fewer than k variables. Okay, what if they're small? Small arity lambdas. So I do this. I do this for the first variable of u, call it x1. Then I have a lambda 1. Then I do it for x2, and I get a lambda 2. And I do it for x3, I get a lambda 3. I get a bunch of stuff on the inside. And I can assemble all of those equations into a matrix equation where the outer L is just lambda in every position. This is a matrix equation. It has lambda values in every position. The first row is lambda 1. The second row is lambda 2. And I have k rows. But since all the lambdas depend on less than k variables, I think of this as a matrix that is not k in columns wide. It's less than k columns wide, but it is k rows. So it's the matrix that's taller than it is wide. And this is a matrix that is wider than it is tall. And these equations all taken together say, if you apply m to a k tuple and then you apply L, you return the k tuple. But L is taller than it is wide. So go back to your undergraduate linear algebra class and think, what happens when I have a matrix that is taller than it is wide? It maps a small dimensional space to a large dimensional space if it's acting on the left. So this L is mapping small dimensional onto large dimensional, but because this composition is the identity, it's surjective. It is surjectively mapping a small dimensional space to a large dimensional space, and everyone should feel uncomfortable about that. Okay, so we should be able to get a contradiction. So here's how we do it. I think of M maps large dimension to smaller dimension, and L maps back. So I think of M as encoding k tuples into k minus 1 tuples, and L as mapping back. Now, I said that the arities is less than k. I didn't say it was k minus 1, but I could fill out some variables that don't matter and make it exactly k minus 1. So I can think of M as taking k tuples, reproducing k minus 1 tuples in a way that is invertible. Okay? So what? So what? We can encode k tuples into shorter tuples without loss of information. Well then, keep doing it. Keep doing it. So I'm gonna encode k plus 1 tuples into k tuples by ignoring the last coordinate. So I know how to encode k tuples into k minus 1 tuples. So I can encode k plus 1 tuples into k tuples and then into k minus 1 tuples. So I can get longer and longer tuples encoded into k minus 1 tuples. Now here's where the contradiction is to that. Ultimately, we end up encoding very long tuples into very short tuples. These have length k minus 1. And how long are these tuples? Some number bigger than k times k minus 1. I find a way to equationally encode very long tuples by iterating this process into short tuples. But we're in a variety where all of our operations depend on at most k variables. And this is an equational encoding. So how do I encode some stuff into the first position? I have to use a term that depends on at most k things. So it looks back and depends on at most k things to compute this first coordinate. Then the next coordinate, it depends on at most k things, this operation that does the encoding. So I get at most k here, at most k here, and k here, at most k here. Who said this? Looks like this, but our paper says this, so I did something wrong here. But I'm encoding, oh, because of the k minus 1. There's only k minus 1 here, right? So it really is this. So I'm encoding very long tuples into k minus 1 tuples, but each coordinate can only depend on a small number of the input coordinates. So I can't encode very long coordinates. But these matrix equations allow us to iterate. We can iterate as many times as we want to encode extremely large tuples and small tuples. So we get a contradiction to the bound on essential arity. And what did we contradict? That is that all of the lambdas have small essential arity. One of these lambdas must actually be surjective. And if you diagonalize the surjective thing, you get your one diagonal term that diagonalizes everything. Okay, so that's a computational trick, but it's a very nice theorem because, let's see, because it allows us to write down a special form for all terms in the variety. There's a special form for all terms in the variety, and it looks like this. Every term can be reduced to d of unary functions. Every term is the unique diagonalizing term applied to a bunch of unary functions. Moreover, the unary functions are all the same, and they're obtained from t just by setting all the variables equal. Okay? Now, the fact that these variables don't agree with these variables is about the variable manipulation I mentioned in the previous theorem. This is a correct statement as written, but you could just think of just t is d of these u values, where u is the diagonalization of t. Okay, now this is easy to prove. I'm going to assume that d actually diagonalizes. I don't care about the variable manipulation, and this is the calculation. If you take what's on the right and it's actually diagonalized, then these variables have correct subscripts, 1 to k. So in that case, if it was actually diagonalized, d of these things is d of, and u is just t of x. So u of x1 is just this, and d diagonalizes t, so I take what's going on down the diagonal and I get t of that. So I do get t of an arbitrary tuple of variables has this expression. Now, it doesn't actually diagonalize, but close enough that this is the idea of the argument. Okay? So any term can be expressed with d and a unary function. And remember what diagonal terms do. They just, they're like rectangular band operations in higher dimensions. The d structure is just, it's a product of sets, and it's you calculate the d value the way you would with a rectangular band operation. So it's something like a higher dimensional rectangular band with some unary functions. That's how far we are at this point. Okay, now I want a unary constant term, some term that the variety thinks is a constant function. Okay, I'm going to assume that I have one and show you how the argument ends. And then I'll go back and show that I actually do get one. Okay, so I'm going to assume I have a constant term, and that means v thinks 0 is a constant function, satisfies the equation saying 0 is constant. And I'm going to define e to be this term. I just take my diagonal term, put x in the first position, and this 0 function in later positions. Okay, what do I get from picking this e? My point here is I'm trying to focus on what d thinks is happening in its first variable. I'm trying to focus on that. And this is the first conclusion. If you take this e and compose it with itself, think of this d of, and then in this x, I got to put e back. So I have to put this into the position for x, and all the other positions are supposed to be 0. But instead of writing 0, I write d of 0, 0, 0, 0, 0. That's the same as 0. Now, because this outer d diagonalizes, it's going to select what happens down the diagonal, and that's x 0, 0, 0, 0, 0, which is just e. So this e is an idempotent function. I mean, it has an idempotent interpretation in every model of v. Okay? And the next thing is, what if I apply e to a term t? I'm going to apply e to a term t. Terms have special structure. So when I apply e to it, e to t, I just take my e was d of x 0, 0, 0, 0. So where I see this x, I put t. This is what t is. but T has the special form, so I wrote it in special form, and all the later positions are supposed to be 0, so I put D of 0, 0, 0 in the later positions. And now the outer D diagonalize it, so I pick up what's happening down the diagonal, and this is a function that only depends on the variable x sub I1. It's a unary function. So E applied to any term gives you a new term that only depends on one of its variables at most. So if you studied tame congruence theory, you already know where I'm going. Or if you read Mackenzie's paper on categorical equivalence, you know where I'm going. And that is I'm localizing. There's a construction in tame congruence theory and in Mackenzie's paper, localization, the localization functor. You look at a variety, you take an algebra, you localize it, means you replace the underlying set with E of it, and you replace all the operations with E of the preceding term operations. The localization functor will be a categorical equivalence if E satisfies Mackenzie invertibility. Okay, so I get a unary algebra. This is a set. These functions that are here, they're all essentially unary. I get a unary algebra. I claim it's a categorical equivalence. For that, I need to know that E is Mackenzie invertible, but everything is Mackenzie invertible. In the minimal variety, minimal Hamiltonian variety, everything is Mackenzie invertible unless it's constant. So as long as this E is not constant, I'm getting a categorical equivalence with a unary variety. And how do I know it's not constant? Well, if I have any term and it depends on all its variables and I start to put some constants in, it's possible to lose dependence on remaining variables, but not in an abelian variety. This is a very non-abelian thing to happen, that if you plug constants in for some values, you lose dependence on other values. That conflicts with the definition of abelianness. So this D, which depended on all variables, if you put zeros in for some positions, will still depend on its remaining variable. I get a categorical equivalence to a unary variety. That's the end of the theorem if I knew that I had a constant term. And this is interesting because I do get a constant term, but I really require bounded essential arity to produce a constant. We have examples of minimal strongly abelian varieties that don't have bounded essential arity, that don't have any constant terms. So it's the hypotheses are just right there to help us complete this argument. Let me explain the idea of where you get the constant term from. This is true for any variety right now. If you want to build a constant term, you look at free algebra on two generators. It has subalgebras generated by each individual generator. If these subalgebras, subalgebra generated by X and the subalgebra generated by Y, contain a common element, say an element that is generated by X and it's also generated by Y, then the variety must satisfy this equation. Okay, and if it satisfies that equation, you can use equational logic and substitute variables for variables and put Y in for both variables and deduce this equation that beta Y is alpha Y. But now you get alpha X is alpha Y, and that's the equation of constancy. So I can take my zero to be basically any term where when you apply it to generator X, you get into the intersection of these two subalgebras. So I will get a constant term if these subalgebras intersect. That's case one. Still have to worry about case two. What if they don't intersect? I take my free algebra on two generators. I take the subalgebra generated by each generator. What if they're disjoint? Here is a picture of that happening. My free algebra on two generators. I look at my generators, X and Y, generate subalgebras are disjoint. Well, remember that subalgebras are congruence classes. So this subalgebra generated by X is a congruence class. The subalgebra generated by Y is a congruence class. There may not be the same congruence, but there will be a congruence that separates them. Because I take the subalgebra generated by X, it's a congruence class. I collapse that subalgebra to a point. That point will not be collapsed to anything in this subalgebra. And when I'm done, I reverse roles and then collapse this subalgebra to a point. It won't collapse anything over here. And now I have after both collapsings, I have a larger congruence that separates them. It keeps this entire subalgebra separate from this entire subalgebra. And in the quotient, mod a congruence like that, these two subalgebras become singleton subalgebras. So I end up with a model in my variety that has two distinct singleton subalgebras. Okay, I have two distinct singleton subalgebras. If we're in case 2, some algebra in the variety will have two distinct singleton subalgebras. And that can happen. That can happen, but not with the hypotheses we're working with. And I will show you why. Case 2 can't happen. Suppose I have a model in my variety and it has two elements that are singleton subalgebras. They're each singleton subalgebras. And I generate something with those two elements. I want to generate a subalgebra of W with those two elements. Okay? How do you generate a subalgebra? You apply terms to your generators. So here I'm taking an M-ary term, putting the elements of G in all possible ways, let T range over all possible terms, and I'll get everything in the generated subalgebra. Okay? But we proved terms have special form. Every term is constructed from a diagonal term and some unary functions. Okay? Now, a unary function applied to a singleton subalgebra will just map it to itself. That's what it means to be a subalgebra. The unary terms fix those points. So if I have put P's and Q's into T, the U's aren't doing anything. The U's aren't going to change anything at all. So I don't have to generate this subalgebra by letting T range over all terms. I just have to generate a subalgebra with D. I just take the operation D and I put P's and Q's in. And this is supposed to be a joke, I guess. There's only one D here, and I'm just putting P's and Q's into its positions. How many different things can I generate? Well, if it's a k-ary function, there's only 2 to the k ways to substitute P and Q into the positions. So I can only generate 2 to the k many things, but I surely will generate P and Q back. So I'm getting a subalgebra of W that is finite. I'm getting a finite algebra in my variety. And we already mentioned earlier that the locally finite case is done. A minimal variety contains a finite non-trivial algebra if and only if it's a locally finite minimal variety. And we're not considering that case. So there can't be an algebra, a finite algebra like this. And that means case 2 can't happen. But case 1 gave us the 0 we needed, and the 0 is what allowed us to construct the categorical equivalence. I'm not going to show you the example because my clock says it's 1:55, and I was aiming to end at 1:50. I'm going to stop there and let Peter take over moderating duties again if he's still here.
Sure. Thank you, Keith. For a nice talk. Do we have any questions? So, maybe I have one, if you allow. So what you just showed in that this case 2 can't happen really used that the locally finite case is settled. You cannot somehow avoid this analysis or with your approach.
Can't, because when you get to the locally finite case, one of the minimal strongly abelian varieties is the variety of sets. And the variety of sets does have algebras with 2 singleton subalgebra. Doesn't have any constant terms. So it's leading you to the conclusion that if you continue to argue further, you are dealing with a variety of sets. Okay.
May I ask something?
Sure.
Of course.
Keith, you started with these definitions and then you said there are 2 types of this minimal strongly abelian, yes? Is this two types related to the fact that when I take your congruence, which the relation you require to be a congruence, say first one, the quotient becomes bigger or smaller than A?
Okay.
Did I say it well?
I did mention two types of minimal varieties, which are the affine and the strongly abelian. Okay, is it the two types you're talking about?
Yes, yes, yes.
Okay, so in the affine case, in general, when you collapse by the diagonal, it stays the same size. So if we have a size, like say it's finite, and finite affine algebra, and you look at a squared and collapse the diagonal, it will be the same size.
Yes, yes, like abelian groups, yes.
Yes. In strongly abelian, we expect the quotient to be larger, but I think there's no theorem like that. It could even be that in the strongly abelian case, if you collapse the diagonal, everything off the off diagonal could get collapsed. It could just all collapse to two things. That's potentially allowed. That would not be affine, but it would not produce a larger thing. Okay, and it would collapse. It would collapse every element to its symmetric pair, but it might not be a singleton on the diagonal. So it's not obvious you will get a strongly abelian algebra that way. But I will say that it's not obviously related to size. It's more related to, if you look at a term operation as a function from a to the n to a, the kernel is a product relation. Okay, that's a better intuition about strongly abelian algebras. That the kernel of a map of a term operation from a to the n to a, that you can define an equivalence relation on each coordinate of a to the n, and the kernel is a product relation of those equivalence relations. So that's a better explanation, I think.
Yes, but I'm trying to make it more categorical so that it will be invariant on the equivalence.
Yeah, so I only know it's invariant under equivalence because I followed through Mackenzie's construction and checked that strongly abelianness is preserved at every stage. It would be nice, I think, to be able to express it more categorically, and I don't know how to do it.
Mm-hmm. All right, thank you. Thank you.
Any more questions, comments?